All right, hello and welcome to Structural Materials. I'm Captain Ricky Besora, your course director and also your structural engineering instructor. This lesson was recently created in 101 and also for 41, so we can have a background of structural materials. So when you actually come here and take WENG481, you dive into design and various design aspects for the class. So over this, I'm gonna hopefully by the end of this, you'll be able to recognize the physical properties pertinent to structural design. I'm going to go over different materials, and not just the materials, also their properties. You're going to start hearing things like yield strength, cross-sectional area, right? Section modulus, different terms that if you're not familiar, by the time you come here and actually take the course, you will become more familiar, but at least this will give you a base so we can get started and actually enjoy our time together doing design. Finally, another objective is recognize the important properties of materials used in structural design. We will maximize those design. For example, why do we reinforce concrete? Right? We're going to mention some items like this. And in wood, sometimes we do look at compression, we look at tension, how we can maximize those so we can use them for our purpose. So first off, here are a couple of the important sectional properties. I'm going to be using A for area, I for moment of inertia, R for radius of gyration. You kind of get the gist of it, right? When we talk about these areas, some of them you can just get from measurements or tables, right? Real quick, you can go to the AISC Steel Manual, which is otherwise known as the Steel Bible, and you can get a lot of those. You can, by just measuring dimensions, you can actually get these values. Now, you can also get this in the bottom, the shear modulus and the modulus of elasticity, by doing ratios. So based on the material that you are using, there's going to be some ratios and relationships that's going to allow you to get your stress and your strains. On the other side, I'm going to have also additional section properties that are going to be pertinent for what you are designing. When I talk about section properties, I'm talking about the beam section, the column section, the wall section, right? So you can kind of understand what those differences are. And then finally, I also have what we call material properties. Right? And that also, as you can see, it included the coefficient of thermal expansion. That's just another property of materials that, depending on where you're at, if it does increase or decrease in temperature, it will expand and contract. So these are very important properties that we're going to be using throughout class, mostly area, moment of inertia, section modulus, the S, and also E modulus elasticity. But in the books and in the slides you will see some other of these physical properties, and it's important for you to understand, hey, here's what they mean, here's the actual units for it. As you can see, I have both US international units, because you will see, even though the course is going to focus more on US units, we also want to make sure that you understand what international units exist. So when you go out there and you hear terms like megapascals or millimeters or meters, stuff like that, you know what it relates to. Stresses. So the stress is basically the internal resistance to external forces. There are actually three kinds of stresses. The first one being tension, right? We're trying to pull things apart. It's going to create a stress that's actually going to try to, as it gets pulled apart, the internal properties of the material is going to try to make sure it stays together, right? Now, obviously, you know that there's stress failures when things break. But in this case, there's one called tension. The other one called compression, the opposite of tension, right? Kind of the same way, but the reactions are a little different. In this case, as we push things together, internal stresses are pushing it apart to make sure that it doesn't deform, or if it does deform, it doesn't break, right? And lastly, we have shear or transverse ripping, where I'm going to put two forces in opposite sides, and it's going to look like I'm going to cut the material, right? So these are just three very important terms of stresses. You'll see, if you remember from the statics lesson, I talk about shear as it were just one force, but in reality, shear is also a stress, all right? Because we use that whole material component to make sure that it can work and resist any shear failure. So again, three kinds: tension, compression, and shear. With stress calculations, in the tension compression, we're going to call that sigma, all right? Sigma is going to be P, which is going to be the force, P over A being the cross-sectional area. So if we have, for example, this column, and we have a force P pushing down, the area of the column is the actual A factor. And based on that, you can get what the tension or compression stress is for this column. Now, a lot of times, like you see here, most design tables simply use the load. sometimes you will see that it will be appropriate to actually use area load, not just point loads. The other one is shear. So shear is something that you're going to learn in the class that we designed to, but we never like shear failures because they're catastrophic. So in shear, we're going to use the term tau, right? It almost looks like a T, but it's really tau, where V is that shear that you calculated in statics, and A is going to be the cross-sectional area of that member, in this case, a beam. So real quick so you can see the differences. Over here, this is considered a shear failure. Why? From the point of the force being implemented to the support, I see a crack that's actually going to break, that's actually going to make my beam break, right? So you have a failure. Whereas in the bottom right here, you have the flexure failure. As you start seeing cracks in the bottom, it lets you know, oh, it may fail and you may evacuate the building. This is why I talk about, you get to see another shear failure here in 3-point load, so you get to see this picture in the bottom. Shear failure is catastrophic, all right? And we need to calculate what it is and make sure that it does not happen. We're gonna prefer flexure failure, like I said in the bottom, because it will tell us, it will give us a little bit of time before it actually fails. Therefore, we can actually go and evacuate the building if we need to, all right? So one thing about shear stress, it's bad. We need to make sure that it doesn't happen. Cool. All right, the other one is talking about flexure stress, right? So flexure is we're trying to bend the beam, right? And that's where you start seeing the failures in the bottom of the beam. Flexure can happen in columns, walls, but usually beams is the easiest way to explain how it works. So when flexure happens, you get to see this kind of triangle occurring. We have a compression section and a tension section. What do I mean? When I bend the beam, in the top, everything is trying to get pushed together, right? All the internal stresses are trying to push together, while on the bottom, they're trying to be pulled apart. That's why when a beam is starting to have a flexure failure, you get to see all the cracks that are coming out, and you get to evacuate the building in time. Whereas, as I told you earlier, in the shear failure, you won't see that. With flexure stress, the formula, it's a little, it may seem intimidating, but it's really not that intimidating. It's MC over I, M being the moment calculated for your beam, C being the distance from the neutral axis to the extreme fiber. We're going to go over that when you actually get down here. And I is the moment of inertia, which, if sometimes you have the book for steel or any other materials, moment of inertia is easily to calculate. If not, you can calculate it if it's a rectangular section or a simple section. And those three values, once you get them, boom, you know what your flexural stress is, all right? And as you can see, I kind of showed you a picture here about how flexural stress looks like. You get to see that in the bottom, you start seeing some cracks, and the failure really occurs in the middle, not at the supports, where that's where shear occurs, right? Finally, another property is strain. So what is strain? Even though, if you probably remember from the beginning, I said that strain is inches over inches. It's really dimensionless, because if you divide inches by inches, there's nothing, right? But I use that to explain, basically it's the change in length over the original length of the member. What am I saying? I got this member right here, right? And there's a force pushing down. Well, as that force pushing down is actually gonna make, you gotta push my member down, it's gonna, there you go. It's actually gonna change the original length of my member, and we're gonna call that the strain, all right? Why is this property very important? You're gonna hear real soon about the Young's modulus, the modulus of elasticity, and that is directly related to strain, right? As my strain increases, my stresses increases, all right? Kind of to understand that, right? As my strain decreases, my stress decreases also. One quick thing about this, just because you push down doesn't mean that there's a linear relationship between as I push down, all that extra unit gets pushed to the side. There's not a direct relationship. It all varies depending on material. So be careful out there if you say, oh, I push an inch down, that means I push an inch to the side. That is not true, all right? Because if you were to look at the internal composition of the material, you're actually feeling little voids throughout the material. And that's why there's not a direct relationship for, oh, as I push down 1 inch, it means it pushes out. So that is not true. Just want to make sure that you all understand that. But the easiest way also to show it is like with a box. As you push down, the box kind of starts bulking up. That's how that strain is behaving, all right? Another one is deflections. So we have compression and tension deflections. Yes, in both ways. But mostly we're going to talk about compression It's usually an easiest one to talk about. But remember, tension, if I have a rod and I push it out, if I exceed that strength, it's going to start deflecting and extending other than its original length. That's why I talk about strain, and also in this case, the delta, which you're going to calculate, is based on the properties. So look at it. It's based on the material properties. PL, P being the load, L being the length of the member, and then AE, if you remember from the beginning, A is the section property, the area, which you can calculate, and E is a material property, the modulus of elasticity, right? You're going to get based on the material. Is it concrete? Is it steel? Is it wood? Is it masonry, right? What do I have? So you need all those combinations so you can properly calculate that delta. And this is just for compression and tension. When you look at beams, it's a little bit different, all right? In compression, it's pretty simple. Usually there's just a load in the top, make it easy. But when you look at beams, well, I may have a point load in the middle. I may have a distributed load throughout the whole beam. And as you can see, the delta changes. However, what doesn't change is the main four factors. I got the force. In this case, it's going to be W because it's distributed, or P over here. I got the length of the member, L, and the length is related depending on what force you're using. I got E, the modulus of elasticity, and I got I, the moment of inertia, which is a section property of the member that you have, of the shape that you have, right? So you still have kind of the same four components, but just sometimes called differently in a different formula, right? What I want to let you know about delta when you come to this class or as you're doing delta calculations. There's a lot of tables out there to help you calculate the delta. Delta is not something you can calculate easily without the proper formula. So what I would just say is save those. You know, if you went back to the statics lesson, you had those drawings that I gave you for different statics solutions. They all have a different delta. Use those to estimate what your delta is, what your deflection is. Don't try to do the whole integration, go do calculus to do this, because you will go down a rabbit hole and probably never come out. Like I said here, the bending deflection depends on the load configuration and the section properties, kind of just to mention it one more time. So now let's talk about materials. Finally, right? So I gave you a little brief intro about some of the section properties, some of the nomenclature we're going to be using, and now we can get into the materials. And the way I want to start this is with the Young's modulus, right? So you've probably seen this before. This one, I like to use the one for steel because it's the one that actually shows all the points throughout it. But I'm going to explain. I'm going to get off camera real quick. I'm going to explain here what is happening, all right? So first, you can see here that we have strain. And if you remember, strain is delta L over L, or the change in length over the original length. Here I have stress, which if you remember, stress is P over A, right? So with those two values, like I said earlier, if I increase my strain, I increase my stress, right? So, and I'm just basically reading the table. If I increase my strain, I also increase my stress because I'm going up through that line. Now, like I said, this is, I'm going to erase a little bit so it doesn't get too crowded. This is for steel. So what's actually happening here? So first, when my material's at rest and there's no load on it or anything going on, I'm right there in that dot in the corner, okay? So right here, there's nothing going on. No stresses, no strain, nothing's going on. As I finally, let's just say I have a column or whatever I have, and I have a load P being on it. As that load P gets put on it, my strain increases on my load. Therefore, I start going through this line, which is going to call my yield strength. And each material is going to have a different, what we call yield point, as you can see here. Yield point, which is basically what it means, the point of no return for your material deformation. Wow, Ricky, that's a mouthful. Can you say it again? Yes, I can. As I load, right? Let's just say I'm loading, and I stop my load right here. If I, for some reason, remove that P, take it out, right? P doesn't exist. This material is going to go back down to its original shape, all right? It basically did not deform. However, let me just erase this because it's getting a little crowded. If I'm loading, right, and I keep loading that material, I keep loading, and then you start seeing the cracks, right? You remember those cracks from the concrete beams and the wood beams? That means I actually passed the yield point of my material, all right? When I pass the yield point, let's say I stop right here, I now have permanent deformation. My material is incapable of returning to its original shape, right? I like to explain this if you think about the paper clip. If you open a paper clip and somebody challenges you to put it back the same exact way it was, that is impossible because that paper clip was made into that shape. Once you change the shape of it, you actually took it past its yield point if you were to talk about it in that perspective, all right? That's why when you go back and forth, you can break the paper clip pretty easily. But anyhow, once I go there, I got permanent deformation. And let's just say right here, you say, uh-oh, I see cracks. Let's just remove all the loads. I'm not comfortable with this. I don't want it to break. Well, when you remove the load, it's actually going to follow the same. That's pretty horrible. Let's try it again. It's going to be parallel to the yield strength line, right? That stress strain line that goes all the way to yield point is going to be parallel. It's going to take me back. And this is what we find out. That epsilon right there, that's going to be my permanent deformation in my material. Okay? So, again, I talked about make sure that you understand what the yield point is. And typically in materials, we want to design so they don't reach yield point. All right? I'm going to talk to you about what ASD and LRFD means once you get out here. But we don't want our materials to yield because if they yield, we are accepting that it's going to be a decreased level of service and it may fail, right? Or, somebody sees a crack in a column or a beam or a wall and now they don't feel safe and somebody needs to come and replace it, right? All this stuff is also based on perception or what we like to call also serviceability of the material. So anyhow, as I keep going down, let's just erase a little bit. Let's just say I keep going up. There's actually a property occurring internally that's called strain hardening. And this actually typically mostly happens in steel. Basically, once I keep loading and loading and loading, my steel, even though this is my yield point, this is not when it breaks. It's when I exceeded the point I'm going to have permanent deformation. This point right here, I'm going to call it ultimate strength. You're going to see that term being used in class, ultimate strength. That is when the material fails, all right? That's why I like to use steel because basically all the materials kind of have this shape and lines, but steel is where it's very evident to see it, all right? So technically, as I keep loading, I can keep loading, and this is actually when the material breaks. Okay? And so, just so you know, we have, I'm gonna be calling yield point or yielding strength Fy. You may also see it as with a capital Fy, depending on which book we're using. And then for ultimate strength, you're gonna see Fu or capital F sub U. All right? So those are basically two very important aspects of it. So as we go, and now you understand how the Young's modulus works and how to use the strain stress curve. Key points, right? I said I have my strain, which is very important. I have my stress. I have my yield point, and I have my ultimate strength, right? And those are basically the key points out there. There's still a lot of discussion in the academic world about what this strain hardening, what's really happening, because it's an internal property to the material. And even though we try to explain it as best as possible, there's no way to positively explain what is really going on. All we can know is that we can get the dimension, the distance of strain, and we know what Fu and Fy really are. So hopefully that makes sense because every time I start with a new material, I'm going to be explaining, I'm going to explain what the Young's modulus looks like for the material. All right, common materials used. Concrete, masonry, wood, and steel. When you come here, we're going to actually learn how to design with all these materials. First one, concrete, concreto, right? So concrete is a great material. We can mold it to any shape. We can pretty much do whatever we want with it. But sometimes when we know it's not really good in tension. Because it's good in tension, we're going to have to put reinforcing steel on it to make sure we have extra strength in flexure, beams, columns, walls, foundations, right? If there's a possibility of having a flexure failure or basically a tension failure of some sorts, then yes, you will be adding, I apologize for that, you will be adding reinforcing steel. So here's the Young's modulus, right? Real quick. As you can see, it goes up to Fy, 4,000 psi or 4 ksi, and boom, brittle failure. So concrete, when it fails, you see an explosion, right? If those of you that actually seen the video of the concrete cylinder, you push, and all of a sudden, boom, it explodes. There's not maybe it starts cracking. Yeah, you start seeing crack, but it hasn't failed. If it truly fails at the yielding, in this case, the Fy is going to equal Fu for concrete, right? Now, what's the pros? I talk about a concrete, right? Hey, it's great compression, low cost. I can make it whatever shape I want, right? All right, fire protection. It's actually fire resistant. A lot of good stuff. What's the cons? Well, it weighs a little bit, 150 pounds per cubic feet. I need extensive formwork, and not that, I need curing time, right? We heard about 28 days strength in concrete. Yeah, there's high performance concrete or quick curing concrete that there is, but that means cha-ching, right? More money. If you just use the traditional concrete, about 28 days to get the full strength, right? Another thing is quality control. There's these things in concrete that if you don't pour concrete correctly or don't even mix it correctly, you're going to get a bad batch of concrete, and you're going to have to come back and remove the whole thing so you can actually re-pour it one more time. All right, so talk about little holes called cockroaches or bad mix design, or if you've probably seen it, sometimes when you have a bad mix design, you leave it there for a week, put the formwork out, and it literally becomes sand and just falls apart, right? So again, quality control is very, very important. A lot of people out there think they can just do concrete. If you have posts and something simple, I would probably say so, but when using concrete for structural applications, you need a good quality control and a good concrete mix to make sure that you have what is required. And then the design codes are ACI, the American Concrete Institute, or PCA, the Precast Association, I believe is the name. So again, that's pretty much for concrete. So when is it used? We use it for everything. I mean, concrete, you name it, we use it. Beams, columns, slabs, walls, bracing, oh my God, it's everywhere, right? So you get to see here in beams, and you get to see some shear studs because we're going to use also concrete deck. But you get to see a lot of them have reinforcement, right? Most of the time that you will see just plain concrete in the Air Force will be in your runways, taxiways. That's because we're making a very thick slab of concrete, and this is just how the way we're going. We're doing plain concrete, all right? So with steel, we have singly reinforced beam, just to get you a little bit of nomenclature. When I have a rectangular section such as this one, I have B being the width of the beam, H being the height of the beam, and D being the depth to the steel. What is the depth of the steel? Well, I'm reinforcing it, and from the top part of the beam all the way to the center line of the steel, I'm going to call that D, the depth of the steel. And then you see over here a cover. What is the purpose of a cover? Well, the purpose of a cover is that rebar that I'm going to put on my concrete to make sure it's reinforced needs, to hold on, right? Just think that you're holding a rebar with your whole hand. Now say I want you to have the same strength with just your bottom hand. Well, if you didn't have a cover, that's what's going to happen. You're only going to have your bottom hand, and you're going to be able to pull. But if you have concrete around the whole rebar, you're going to have a good bond. Is what we kind of call a good bond in concrete. A good bond, so I make sure that the rebar doesn't pull out, all right? Because in the end, you'll see, I'm going to talk about it in a second, I want my steel to fail first before my concrete, all right? So, and then when we talk about my tension bars, my rebar that's at the bottom, I'm going to call that area of steel, or A sub S, right? A sub S. It's going to be the area of steel use. And so why are we reinforcing concrete? Like I said in flexure, we're pushing that beam, right? And as that beam pushes, the top is in compression, the bottom is in tension. That's what we're going to call the top, the zone of compression. We're really rebar is not necessary. Now I'm going to talk, when you come here in concrete, I'll talk to you about when is it necessary for concrete. But for now, let's just talk that rebar is not necessary. But in the bottom, hey, yeah, concrete is horrible in tension. We know that. We're going to have to put reinforcement on it, all right? And that's basically the mentality behind it. And here's what we call the witness stress block. And I mean the whole community in concrete. And this is a basic understanding of how concrete works. So first off, I'm gonna start blocking, and as I speak on it, I'll step back. The first one is I got my cross section of concrete, my rebar, my depth of it, and you see this little dashed line here is going to be called the neutral axis. What is the neutral axis? That is the exact location where my compression is going to switch from compression to tension. Because if you look at flexure, right, your top is in compression, your bottom is in tension. Therefore, somewhere inside of the cross section, there's going to be a transition, right? A transition point between compression to tension. All right. So what is going on, right? So I talk about the neutral axis, and here you see it, right? You see first off the strain diagram, and you get to see that I have the strain for concrete. the ultimate strain of concrete, which is going to call it 0.003. That's a really, really small number, right? Why do we have to use really small numbers? Because again, think about serviceability. Would you like to work in a building where every time you walk, you start jumping up and down? No. And I'll explain that a little bit better when you guys and gals actually come out here for 481. And the other one you see here is the strain of steel. And we want to make sure that the strain of steel is larger than the yield strength of steel, but is smaller than the concrete strain. Why? So typically you will see that our steel strain is going to be 0.002, which is smaller than 0.003. We want our steel to yield first. All right, don't worry. When you get back here, we're actually going to go through the Whitney stress block one more time. But it's very important that you understand that we want the steel to yield first. Because if the steel yields, that means I start seeing cracking in my concrete. That means I have time to escape my building. If my concrete yields or breaks, right, brittle failure first, I would not have time to escape my building. Right? That's what's going on here. As we go through it, we look at it and we say, well, what's the actual stress block, right? What's the ultimate stress blocks? Well, I know my top is in compression and my bottom is in tension. But you already said that concrete sucks at tension. Yes. Therefore, what's really holding the whole beam in tension? The steel rebar. And that's why instead of you seeing a whole area here, you see like 3 lines. What are those 3 lines? I'm talking about the 3 rebars, but if you have 2, then it's 2. If you have 1, it's 1. In essential, it's just 1 line. The rebar is the only member that's actually holding in tension, whereas in the top, above the neutral axis, the concrete is holding in compression. And we're going to start measuring those distances. And you're going to see this value of 0.85 F prime C. F prime C refers to the concrete strength to the concrete strength. Right? So that's why you start hearing 4,000 PSI, 5,000 PSI, 2,000 PSI concrete, right? That's what it means. Okay? So with that, we say, well, this is kind of like a parabolic shape, right? And I'm going to ask you, hey, how do we make sure that we want to make sure that the compression and tension equals? Well, that's a kind of hard shape to get. What if I simplify it? And that's what Mr. Whitney, right? Whitney stress block did. He said, let's simplify where if I make this square block and I just find a value for A, which is just a formula you're going to learn how to do, and I multiply A times 0.85 F prime C, I can get what the whole area, pretty close estimate what this whole area is by just applying a rectangular shape. In the end, Fy is still there, right? Even though the actual stress distribution is nonlinear, we're going to assume it's linear, just like you see here, just for our sake, right? To make it simple, to make our calculations a little more simpler. We don't want to have to do calculus every time we do a design. Okay? And finally, we're going to then make sure that we have a compression strength and a tension strength, ASFY. AS mean the area of the steel, Fy mean the yield strength of steel. And I'm going to make sure that, first of all, we're going to use it that they're equal, but in reality, we want to make sure that our compression strength is a little bit larger than my tension. And that's where the concrete art comes into play. We play a lot with how close do I get my concrete strength to my yield strength, right? How close, and that's where economics comes into play and everything. So again, it looks like a linear strain distribution that in reality is nonlinear. We simplify it with a block, and then we finally can calculate what my concrete strength and my tension strength is. And just to show it one more time, here are all the values that we simplify, this simplification of the Whitney stress block. We have this area is going to be 0.85 F prime CB. We have A being beta 1C. Again, all these values, we're going to be able to discuss them once you come to class. And then we have the D being the depth to the steel, and then tension being the area of the steel and the yielding strength of the steel. All right? So again, this is the Whitney stress block. This is the basic methodology of concrete and masonry. If you understand the Whitney stress block, any problem in concrete, you can approach it, because any problem in concrete basically uses this fundamental practice to explain behavior of concrete that's reinforced. Okay? So anyhow, with that, why do we use reinforcing bars? Well, first of all, if you remember, concrete was like 4,000 or 5,000 psi. Well, one little itty bitty bar can be 40,000 to 40,000 or 60,000 psi, right? So a lot bigger, right? 10 to 15 times bigger. Do math on the fly. That's what happens. And it's size by diameter. For example, a number 8 bar, it's 8/8, or 1 inch. A number 7 is 7/8 of an inch. A number 6, 6/8 of an inch, right? Now that's for, again, we're using US versions. So we use rebars and we put it in the tension zone so we can reinforce it. Finally, when you look at rebar, one detriment of rebar is that it starts getting heavy, and you need that cover space, and you need to increase that. So when you look at that, you're going to have this table on your book, on the structural book, and we have, for the different sizes, you have nominal weights, diameter of the rebar, and the cross-sectional area. I will ask you in class, and I will repeat it here, always use the cross-sectional area provided here. Because if you look at the rebar, it has little indentations on it, right? And those little indentations actually are accounted for in this cross-sectional calculation. If you try to get the cross-sectional area of a round rebar being PR squared, you're going to be off by a little bit, right? It may be a little bit, but here's the thing. In economy engineering, when we're designing concrete, we want to use every single little square inch of steel that I can so I can save money, right? If you do oversimplifications, you're going to get overestimates. And that's why I'm going to ask you during class and in practicing concrete, we always use the table of cross-sectional area. We don't actually calculate the cross-sectional area based on a round rebar. All right? As you can see, we can go pretty big, right? Number 18 are huge. 18 over 8, that's a pretty big rebar, correct? So anyhow, just so you understand how it is. Design philosophy. Like I said with the Winning stress block, once we go past that neutral axis, the concrete is doing nothing. All the tension is being carried by the steel, right? Therefore, we're going to place the steel rebar in the tension zone to resist flexure and carry the load. Additionally, we talk about the strain, right? I told you that the strain of concrete is usually 0.003. Where we're going to make our strain of steel around 0.002, you can see that those values will vary, basically smaller than the strain of concrete so that steel yields first. Steel yields first, all right? If you have a tough time understanding this, don't worry. We're going to go a little bit over it when you get here. But concrete is designed so steel yields first, and then concrete fails, right? But we want that steel to yield first so we can give us a shout-out. Hey, I'm breaking. Evacuate the building, right? As steel yields, concrete will crack, showing the stresses. But when concrete fails in tension, it crushes, leading to catastrophic failure. Just think about, you never watch this, literally Google concrete compression test, and you will see those exploding blocks. And that's why we don't like our concrete to fail first. We want our steel to yield first. And here's the kind of the example to bring it all home, right? So if you remember, I mentioned some key components, right? I talked for steel, Fy, F sub U, and for concrete, you have Fy and F sub U right here, all right? One thing you will see is, first of all, that's the strain of concrete, right? Versus, look how small the strain of steel is as compared to concrete. So one of the things I mentioned to you is I want my steel to yield first. Therefore, my strain has to be smaller than concrete, all right? So because my strain is smaller, my steel, as I keep, as I have, let's just say this is a column or whatever that I have, as I load it, my stress and my strain for steel and concrete are going to increase the same. Sorry, my strain for both concrete and steel are going to increase the same. So if my strain in concrete reaches this point right here, that means my yield, my strain in steel reach all the way up here. Therefore, I have a higher stress in my steel, and my steel is going to yield first. All right? And also the reason why I show this is to you to understand why do we reinforce. You get to see that the stress of the stress capacity of steel is way, way, way larger than the yield capacity of concrete. So hopefully this kind of makes you understand a little bit about it. Get you started. Now masonry, right? So masonry is just kind of a subsection of concrete, but we have clay bricks also. So I'm going to go a little bit about masonry because you will be also able to design using masonry in this course. So masonry, right? So first of all, the yield strength varies from 2 to 8 KSI, right? Or 2,000 to 8,000. Why? It depends on the brick that you're using. Is it a CMU? What type of CMU? Is it clay brick? What type of brick? All right? So that is very, very important to understand what type you're using so you know what that stress is. What are the pros? People love it. It's low cost, very easy to build. I mean, as you build the wall up, next day you can start doing other stuff in the wall. It's very, very quick and easy. However, the cons, a lot of labor intensive. I don't know out there, but I've worked putting up brick and CMU walls actually, and it gets tiring. After you're 3 feet, 50 feet long, you got, oof, I mean that back's gonna start to hurt. You get tired. So very labor intensive, but it's very easy to construct as opposed to having to do all the foam work and pouring concrete, and then once you take the formwork out, you have to cure it and all that stuff, right? Also, the appearance is very popular throughout the U.S. to have brick veneer walls. It looks pretty. Architects love it. And it actually is great for those mechanicals out there. When you have concrete, it's also good for when you have an air gap for your brick veneer for temperature shifts. So, in design, it's very similar to concrete, very, very similar. The only thing we're going to add in design when you get out here is we have the mortar, and the mortar is very important. And we have reinforcement sometimes, depending on the number that we reinforce. I'm going to go over that in a second. So when is it used? Lintels and some beams. A lintel, just so you know, is basically an opening like a door or like a window. By the time you start going into very large, it doesn't really make sense to use masonry to do beams. It really makes sense to do concrete or steel. But just so you know, it does exist. Sometimes we want to use masonry for lintels just so we can keep the pattern and it looks nice. Columns, right? You get to see here columns, very, very effective use. They're very good in compression and they're lighter than concrete when you think about it. And then finally walls, either reinforced or unreinforced. So like I said, there's two types, right? We got bricks and we got CMU. For the bricks, we have solid and hollow. And when you talk about hollow, it means that we're going to start putting holes in it to make it lighter, right? Again, if I think that with the hollow I still have enough area to handle the compression, then I'm fine. All right? Different grades, severe weathering, moderate, and negligible. Depending on which one you have, you see that your strength varies, all right? Now you saw that I showed you in the first slide, it's up to 8,000 PSI strength. Yes, I only show you these guys here, but you can get higher strength bricks that can go a little bit higher. Then the other one is the CME, or the concrete masonry unit. Basically, it's formed by zero slump concrete. I'll show you in a second what that means in a little drawing. It is accelerated for steam curing, and this CME, even though it's heavy, it's lighter. I mean, if you basically pick up the same size block of concrete, you're probably going to break your back, as opposed to you can pick this sucker up and put it up and reinforce it as you need to, all right? We're going to call F prime M, or the compressive strength of masonry, right? You talk about F prime C for concrete, F prime M for masonry, all right? For the clay bricks, here are kind of some dimensions that you will have in your printout so you can look at. There is a difference from nominal and actual dimensions. Why the difference? I'm just going to use this example, for example. The nominal dimension of a concrete block is 8 by 8 by 16 inches. But if you actually measure it, the actual dimensions of the brick is 7/5 by 7/5 by 15/5. So why do they use 8 by 8 by 16? Because if we count the mortar and how we're going to put it on the wall, it actually becomes an 8 by 8 by 16. All right? But when you make your calculations out there, it's going to be based on what your actual dimensions of it is for compression and for tension. So don't worry, we're going to talk about that. It's just understanding that in this realm, there is actual dimensions versus nominal dimensions. And as you can see, it also comes in various shapes and sizes, whereas the main one right here, you see at the bottom, the standard brick, which I have here. Why is it the most common? Because I can make other shapes if I have the standard brick. So therefore, I'd rather have the standard brick, and I cut or hammer away to make the shape that I need when I'm downrange or downside. All the masonry terms that I have here, you get to see I have the course, which is basically means the row, right? So when I say it's a 5-course wall, it means 5 rows, all right? Then I have the width, which is essentially the width, but the width means the brick. If I have a 2-width wall, that means I have 2 bricks side by side, or 2 CME blocks. 3 width, triple, and we keep going up and up and up. Stretcher means how I lay the brick out long ways. Whereas the header, I put it the short way, but then you see I will need a double width at the bottom wall to make sure that I can make sure it's not hanging off of it. I also have row lock, bull stretchers, and finally soldiers, where I just do them standing up. So again, it's just masonry terms. What you're probably going to be using in this class are mostly going to be the courses, the width, and the stretchers. You're going to kind of stay in this range up here. We're not going to want you to get fancy, but just so you know what it means when you go out there and start doing different projects. and bond. So bond, based on how you place all this, you get to see that the pattern from the outside really looks different. We're gonna call the pattern in masonry the bond, right? Don't get confused because I use the term bond in concrete to mean how strong is it attached to the rebar of the concrete, right? In masonry, the bond basically means what pattern do I have, right? Running bond, basically I interlock them. Common or American bond, well, I have some interlocking, but I also have some stretchers in between to make a certain pattern and so forth. You get to see how all of them are. However, UFC 330-101, which is a structural engineering UFC, specifies to you that you will use running bond for shear walls or basically load-bearing walls, all right? So that's where our focus is going to be in the class, mostly running bond being the most used for us because we're going to be using them for structural aspects, not for visual aspects, okay? Another masonry term is joint reinforcement. So every certain amount of courses, we're going to need to reinforce the joint, all right? And so how do we reinforce it? We have ladder type or truss type. Basically, we're going to put that there with the mortar to give it a little extra strength, right? There's some that's made out of aluminum or steel. They're just there to give an extra reinforcement over that joint. So one thing is don't use corrugated metal, right? When we're downrange, there's a lot of corrugated metal and you're going to feel inclined to do it. Don't use corrugated metal. It's not allowed per UFC 330-101, which is a structural engineering UFC. Then we have mortar, right? So we have concrete and everything, but we have mortar, which is what's going to be in between all the courses, right? Those bed joints. That little, when you look at a wall, that little bit in between, that's called mortar, all right? And let me go through this in the bottom first, right? So we talked about how for masonry, you have concrete slump, which essentially we put concrete in this cone right here. We put the concrete, we lift it up, and then you have a slump of 2 to 6 inches to concrete. For mortar, we're going to have a slump of 5 to 8 inches, and for grout, we're going to have 8 to 10 inches. And what is grout? Well, grout is how we're going to, let's just say you calculate it and you need some flexural strength because your wall may topple or your lintel or your column, then you're going to fill some of the holes with grout, all right? But as you can see, grout is very, very, very watery. Why, right? Very, high slump. Why? So why is it very, very high slump? Because when you pick up CME, you're going to see that it has a lot of little voids, right? So if we're going to think we're going to fill that with a reinforcing bar, or we need additional strength, we're going to make it a little watery so we can fill all those little voids, right? Ensure that we have the strength that we need and the cross-sectional area that we need. If I don't have it too watered down, I'm not going to be able to fill all those voids, all right? That's kind of behind it. And then if you remember, I said that CMUs are made from zero slump concrete. That means that when you raise that cone up, the shape kind of stays the same. Essentially, it's not going to slump anything. That's what CMU is. Very dry concrete is what I like to call it. All right, so that's just to explain that. Now we talk about mortar. And with mortar, which we're going to be reinforcing, one of the biggest things with mortar is it provides flexural strength or tension strength between the mortar joints, right? Because there's a possibility that if somebody pushes the wall, the mortar is the only thing that's going to keep it together. All right, so you're going to see that even though we're going to have compression strength, in the future slide, I'm going to show you also what tension strength you have for it. So one thing to help you out for mortar, this kind of acronym say Mason work. And basically you see type M, S, N, O, or K. And you can see here, type M has a compression strength of 2,500, S 1,800. And basically it kind of takes you from the strongest being type M to the weakest and no longer used anymore, type K. All right, so it's a good thing to kind of remember. All right, a Mason work, I understand what's the strongest. So if I have type S versus type N, you know that type N is weaker than type S. The other thing is, this is kind of how you make your mortar, depending on what type you're using, all the different, right? 1 part Portland cement, 1/4 parts hydrated lime, and 3.5 parts of sand, all right? So as you can see, it's per volume, so depending on what volume you have. All right? Now that we're done with masonry, we're going to go over to steel. Steel is one of the greatest materials ever made. We make it the shape, and we're pushing the boundaries of our design. That's why you start seeing some weird shapes like hollow steel tubes, I-beams, squares. We're going to maximize the theories behind stresses so we can use steel properly. So I already showed you the Young's modulus. Steel, usually it yields at 50 KSI, but it breaks at 65 KSI. Pros, it's very high strength, right? Extremely high strength. It's efficient. We're gonna only put the steel that we need. We're not gonna give you a cross section that's huge, right? With concrete, I told you, bottom of the neutral axis, that concrete's doing nothing. It's only holding together the rebar. It's really not doing anything, right? Well, we know that happens, so therefore in steel, we're gonna maximize how much steel we're using to make sure that we don't use excess steel or unnecessary amount of steel. It's controlled by the manufacturer, so you can just order a shape and know that you're getting an A992 steel that's gonna yield at 50 and break at 65, right? So a good quality control because you get it from the manufacturer. Very quick to go up. I mean, you can put a couple stories up of steel if you got a good crew in a day. Ductile, that's actually one of the good properties of steel, right? So ductile means, I told you, why do we put reinforcing in concrete? Well, it's gonna yield first, but it's not gonna break. But if it yields, my concrete starts to kind of crack so I can have time to escape, right? Well, even if I just use plain old concrete, I can start seeing some bending, and that's when it becomes ductile. It can actually give us notice. The other property about ductile that's very likable is in seismic applications. Therefore, the building is gonna start shaking. I have steel. It's not gonna break. It may go past yielding, but it's gonna have a ductile version. The best way to explain this is if you have that, you have the material that you pull apart and it becomes very thin, but it didn't quite break until the very end. That's a very ductile material. And also, they're recyclable. Steel is recyclable. So therefore, if we tore down an old building that's steel, we take that steel, we melt it again, and we reuse it. Very good. However, as a con, high cost, very heavy. It's pretty much the main two things. Oh, and also corrosion. If you are using a steel in an area that it's going to be prone to salt, you may have to use a special type of steel for it. So the design calculations that we use are AISC, calcs, tables, and charts, and there's also manufacturing tables. If you go to a steel manufacturer, you can just ask them or just Google them, and you may find their website, and they have all the shapes, their strengths, their section properties, and everything you need for your design. Another con is limited to catalog, right? With concrete, we can make whatever shape we want. With steel, not quite. We're limited to what the manufacturer can do. There are some new manufacturers coming up about making whatever shape you want, but that costs you money, right? So you gotta make that decision. With steel, we have a lot of different types, right? Wide flange, standard, bearing pound. This is just a little bit of all of them. However, we're gonna call, for example, a wide flange W24 by 62. What does that mean? Well, the 24 means the depth, 24 inches. And the 62 means the weight per linear foot. So in this case, 62 pounds per feet, all right? And that's one of the nice things about steel. You're gonna see that in the shapes, they're gonna write down this nomenclature, WS or whatever, and it's gonna tell you. So therefore, if you go look at a building and you say, hey, I'm gonna use an S12 by 35, yeah, you can verify. You can just, I got an S12 by 35. Let me just double check in the tables. Yep, depth is 12 inches. Weight is 35 pounds per linear foot. However, I will just caution you that for small sizes like this, 2 feet or under, yes, that's typically the depth is going to be the first number and the weight is going to be the second number. However, once you start going to those girders that are like 5, 10 feet deep, that kind of starts going a little bit off range. So just for your understanding. And so when we talk about the flange, the steel beam, I got W for mean wide, S for standard, M for slender. That's just the nomenclature you're going to see at the beginning, right? Like we saw here, WS or HB. Then we have what we call the nominal depth of the beam, right? So for example, a W24 by 62, even though it's 24 inches deep, in reality, if you go to the tables, it's really 23.7 inches deep. And that's why I kind of hit that. Sometimes it's good for you to actually go to the tables and double check that, yes, this is true. But if you're out there and you're just seeing that, you can make the initial assumption that that is the correct depth. But you can see as it gets heavier, at W24 by 370, it's actually 28 inches deep. It's just how the nomenclature works on it. So the other aspects here is B is going to be the width, and D is going to be the depth of the section. And I want to mention a couple of things here. This part right here is going to be the flange. And this part right here is going to be the web. And then this is also the flange. So you got top and bottom flange, and then you got the web. So, because you're going to see that in some calculations we're going to be doing, I'm going to ask you maybe the whole cross section, or you may just have to ask yourself, oh, what's the area of the web, or what's the area of the flange, all right? So, again, one thing that I like to see, that I want you to understand is, why is it an I shape? Well, if you remember from the Whitney stress block, you know that the top is in compression and the bottom is in tension, right? Well, steel says, okay, I understand that component, therefore, why can't we just maximize it? What does that mean? If the top is in compression, let me just make it wide at the top to handle all that compression. And then this whole transition zone, right? Neutral axis happens somewhere over here, but my maximum tensions happen at the bottom, therefore, let me just make the top and bottom very thick. And then I just need the web to transfer the load from the compression zone to the tension zone. Right? So this is where you see where if you had concrete, you had to fill this whole block up, or if you have an I section, it will be a little more thicker, because concrete is also trying to maximize by doing I sections with concrete that's reinforced. And here's other beam designations just for your essay. Most of the time, you're going to use I-beams or angles is what you're going to see mostly out there. Anything other is just based on the project or specialty that you're doing. Beams, however, when they fail, one of the failures is buckling, right? So in this case, we have a web. The web is very thin. If you ever pick up a beam, a small little beam, you can see that it's kind of flimsy, and you see, wow, that little, 1 inch of web, that's all, right? And this is going to be handling thousands upon thousands of pounds. Well, that means that the web needed to be stiffened, essentially. So we need to put little stiffeners on it, or bracing, so that this doesn't happen. But this is called buckling of the web. Basically, a very thin web, narrow flanges, it's weak laterally, and you can start seeing shaking. The other one is the deflection, right? So when you see steel, a lot of times you see it kind of camber up, right? It's kind of, instead of being deflected to the bottom, it's deflecting to the top. Why? That's just how it kind of comes out of the fabrication, so you got to account for that. You can get a very nice straight piece of steel, but as you can start getting longer, it starts having a little camber. You need to account for that, and as you push your load, essentially you're going to take that guy down and start making it flatter. So you need to understand what those are, especially in the span to depth ratio. And then finally, connections and supports. I'm going to talk to you a little bit about what they are at the last slide. Joists. So joists are also maximizing the space. I say, hey, I understand that I'm only going to use the top and bottom for transition, the web for transition. Therefore, can I just make it a truss? And so we have joists that are basically trusses, and they're designated as 20K7. The 26 means the overall nominal depth. Like I said in the beginning, though, it's always good practice to, yes, 26 inches, got it, but let's just go back to the manufacturer tables, or actually check it out and make sure that it's actually 26 inches. K is the type, and you may look at it, this is actually a K. Why? Well, here you go. That's my K right there. So just so you understand how it kind of works. I don't know why they just didn't call it triangles. And then number 7 is the class of size. Basically, the higher it is, the heavier or stronger it is. And now I'll talk to you about steel connections, right? So I told you that one of the biggest aspects about steel is how it's connected. Steel is great, but the connections are usually their weak point, right? Because that's where it got cut, somebody tried to manipulate, it got heated maybe, or something happened, it got dented. So there's a lot of different connections. Riveting used to be very heavily in the 20s, 30s, and 40s. You get to see here, it's very pretty, but it's not very effective, right? So I don't expect any of you to actually be using rivets for your designs in this class, or at all throughout the Air Force. The only time you will see rivet occurring is in historical facilities, if they indeed had rivets. But a lot of times what they try to do is they try to get an exception to the rule and use bolting, because bolting is much more effective than a rivet. For bolted, you have either snug tight or pre-stressed. Snug tight means it's tight enough, got it. It's not going to squish the whole thing, but it's tight, so it's not going to actually fall, right? So when things shake and you start seeing bolts falling on you, that's because that bolt was actually snug tight, but it wasn't snug tight properly, all right? So the other one is pre-stressed, where I'm gonna make sure that it's super snug tight, and then I'm gonna go on it, depending on the engineer, it could be 1 whole turn to 2 whole turns. Apologize for that. 1 whole turn to 2 whole turns, and I'm gonna squish that guy together. What is the pre-stress trying to do? It's trying to make it seem like there's not a hole by squishing the material together and making the transition seamless, right? And you might think, wow, pre-stress is always better. It depends on what behavior you are accounting for. I like to use pre-stress a lot, but again, what is your behavior? For example, snug tight, I'm going to use this when you talk about wood or other stuff, like say you have your home desk. A lot of times in your home desk, you want it to have snug tight. Because if you try to pre-stress it, you're actually going to break the material. Because the material is not designed to be pre-stressed, right? That's just a quick example for you to understand how that works. And then weld it. Yes, you can weld. In the Air Force, I typically don't recommend welding unless you got an experienced welder. Because in the structural realm, they get certified for not just the type of welding, tack welding, fillet welding, partial or complete, but also how they're welding. What do I mean? Well, you can go to a class and get certified on how to weld standing up in a vertical line. But you also need to get certified of if you lay down and do this. Or if you're hanging, right, you're 30 feet in the air welding, you need to be certified for that. Or if you're kneeling down in the bottom, each individual weld has a different certification, right? So again, because you're using welding as a structural member. So a couple of different welds is tack welding, which you see here, which essentially we say it's not really going to be a structural term. We just want to make sure that it sticks together, right? So you're going to see it in covers, things that are not really structural. A fillet weld means I'm going to go kind of straight, but as you can see, this is a fillet weld right here. You get to see some gaps, but I'm only going to, I literally just put two pieces together and I follow it. And that's what people typically, if you actually go to the welding shop, that's most of what people do. Because partial joint penetration means I'm actually going to have to, I'm going to bevel, it's called bevel. So I'm just going to draw it out real quick. So I have a piece here and a piece here that I want to weld. Well, if I want to get a partial joint penetration, I need to do this, right? So this guy is going to look like this, and this guy is going to stay like that. Okay? And I'm going to feel a little bit more that guy right there. So like you see right here, right? Partial joint penetrations where I'm not actually going to go all the way through. I'm going to feel half of it just because I can't really get access to it, right? Whereas the complete joint penetration is I need to get that filler material all the way through both my materials, right? Whether it's top and bottom right here or top and bottom in this way. And that's just to make sure that it transitions completely. They are all effective for their intended purposes. Obviously, complete joint penetration being the strongest one, it's as if we're trying to tell the material, the steel, there's not a cut, right? Just like we do the pre-stress with bolts, we try to do it with complete joint penetration. But that is harder, right, than say partial or fillet welding. So you see a lot of those out there. I typically recommend if you are not familiar with welding or you don't know how to weld, just go with bolting. Bolting is very simple and easy to construct. Finally, the last material is wood. As you can see, wood has, a lot of shapes, right? Not just the shapes, also the grain direction. So real quick, materials in wood, one of the things here, and I put it right here, this is for Douglas fir. Because why? You can have pine, you can have oak, you can have different types of wood that have different types of behavior. So that's one of the key things about wood. What type of wood do I have? Because pine doesn't behave the same as Douglas fir, doesn't behave the same as oak. All right? However, as the pros, it's low cost. We use it across the U.S. greatly, right? We love building with wood. People can figure it out. It's not a big deal. And you can actually get kind of structural pieces of OSB. I'm going to talk about what those means, glue-lam, and get stronger sections. What are the cons? There's limited design scope, right? It's very difficult nowadays to get a very large section because you can only get as large a section as the tree creates, right? If not, we're looking at the manufacturer alternatives like glue-lam or OSB, stuff like that. That basically, we take a lot of scraps, we glue them together, and then we give you a larger piece. Right? So that's one of the things that we're actually having issues nowadays that wasn't an issue, say, 50 to 100 years ago. Fire and decay protection, right? We have rot. If it burns, fire burns. Those of you that have live in the northern climate or cold climate, you like to have a little fireplace sometimes and burn some wood and stay warm. Anisotropic is, the behavior, depending on how you cut it, has a different behavior. I want to talk about that's where the grain direction comes into play. Right? And finally, like I said, properties depend on species and dimension. But one of the big things why we still use wood a lot today is that it's very easy to build. And so there's tables in the IBC, Chapter 23, International Building Code, but there's also NDS, which is the National Design Spec for Wood Construction. They're the ones that actually help you know how to design with wood. With wood, the biggest issue I see with wood, so wood is not really difficult, it's just understanding the nomenclature and what you're using. Well, the nomenclature is one of those things, right? There's a stud, there's a trimmer or jack stud, a cripple, a header, a roof rafter, right? There's a lot of different nomenclature. So if you are working with wood, just understanding the nomenclature is half the battle. And I just circled in red what I think should be the ones that you should know kind of by heart. If you're not familiar with wood, these are things that will help you out greatly. All right, there's other ones like bottom pan, rough sill. That it depends on what you're using. That's not really something you need to remember. Something can refresh your mind. But in reality, just understanding the ones that I got circled in red will really help you understand how to the terminology works. And here's another drawing, just in case that 3D was kind of confusing. You get to see it in 2D also. With wood, again, we have the same issue we have with masonry. There's actual sizes and nominal sizes, right? So a 2x4, hopefully I'm not blowing up your mind, but a 2x4 doesn't actually measure 2x4. It actually measures 1.5 by 3.5 inches, all right? Right? 1.5 by 3.5 inches. So why is that? In this case, I can actually explain why the difference. So when wood is cut, it's cut wet, right? You know, you've seen those videos of they put it down the river, they pull it from the river, and they start cutting in different pieces. That's why it's 2x4, because yes, when it's wet, it is a 2 inches by 4 inches. But as it's dry to about 80% humidity, it shrinks to about 1.5 inches by 3.5 inches, all right? So that's kind of what it is. Here's a rule of thumb, because sadly, you can't just say always take 1/2 inch. The rule of thumb is always, if it's less than 7 inches, take 1/2 inch off. If it's 7 inches or up, take 3/4 inches off. But don't always use this rule of thumb as the law, the rule. Again, it's a rule of thumb. It's meant to help you out. If you have a question or a doubt about the sizing, just go to the MDS or the IBC or the manufacturer and actually get what the actual size is. Okay? There are 4 types of basically of structural lumber. We have dimension lumber, which we talk about thicknesses being 2 to 4 inches. Now, with a width of 2 inches or more. That's what we're going to call dimension lumber. The other ones are beams and stringers. Well, if I'm thicker than 5 inches or greater than 2 inches also, or the thickness of 7 inches, then it is graded for flexure. That's why we're going to call them beams and stringer. It's going to be behaving better for my flexure beams or members. Posts and timbers are basically 5x5s or greater. We're going to use them mostly as columns or, like you see here, posts. And then finally, decking. It's 2 to 4 inches thick, tongue and groove. You can get to see little tongue and groove back in the day, but you can also see the plywood decks that we're having nowadays. Design value. So this is the thing with wood that may be a little intimidating for you at the beginning, but once you understand how wood works, it's not really intimidating. You just got to know which one applies, right? So you know how we talk about the yielding strength, Fy and Fu? Well, in this case, we have different strengths, right, which is very closely associated to the yield strength based on how you're loading your material. So FB means bending stress, but FT is tension parallel to grain, right? And don't worry, I'm going to actually come out with a couple of wood pieces so you'd understand a little bit better when you get here what the grain really means. But you just need to understand how you're loading your member and how you're placing your member, okay? You know, a lot of times when we use 2x4s for decking or 2x6s, we place them, you know, kind of the 2 by section on the top and the 6 inches along the row. Why? Because we know that it's better behaving that, it's better, my moment of inertia is higher, therefore I have a better strength. But which one do I select? Well, it depends on how your grain is, right? Is my grain parallel to grain or is it compression parallel to grain? So just understanding how each one of these works is just, once you understand, like I said, nomenclature and knowing which one to select for your loading case, then you're done. It becomes really, really simple at the end. That's why a lot of people still today design with wood, because they understand what this nomenclature really means. Okay? And then finally we have the modulus of elasticity, E, but they like to use an E minimum. Basically, it's a use for stability computation. Why? Wood is harvested. Yes, it's Douglas fir. Yes, it's oak. Yes, it's southern pine. But in some cases, like beams and column buckling, we know that there's a certain aspect that it can range, that E, right? Because yes, I got oak that was made in one part of the US and I got oak made on the other part. Sometimes they're just going to call it the same. If that's the case, we like to use E minimum for certain members because we know there's going to be some sort of difference in the E, and that E is not always precise. All right. So anyhow, that's why you're going to see E minimum. And when we go through the wood class, you're going to get a better understanding on it. Finally, the design values, right? So I kind of mentioned a bunch of them, like bending, tension parallel to grain, shear parallel to grain, and you get to see how all the values vary. Not only does it vary based on the type of wood, it also varies. Do I have dimension lumber? Do I have timbers? Do I have, it comes down decking? What do I have? And based on that, it actually gives you a different value. And as you can see, the values are in PSI. And here's what I told you the last part. You got the E, but also the E minimum depending if you're doing different items. So one thing is wood is made in ASD. I'm going to mention that when you came here instead of LRFD. So you can design in LRFD, but still wood design is mostly done in ASD. It's still effective. It's not a big issue. So anyhow, with this table, just understand which numbers you're using, which values you're using, so you can make the right determination. Other thing, factors, right? And you're going to see this table in your book. I'm going to go a little bit over it also, but where am I putting it? Is it going to be a wet location or a dry location? Is it going to be freezing or is it going to be warm, right? All this stuff actually affects it. And all these factors, obviously, you only select the ones that are applicable to you, right? Applicable to your use. You actually use some correction factors that can either increase or decrease your load for your design, all right? So don't get scared because you see so many factors. Again, you only use the ones that you need for your design. But this is why wood, again, is another reason why it's heavily used, because you can kind of manipulate. Well, I'm really using it for wet use only, so I'm going to decrease this. We're done, right? Or there's a lot of these members. There's a repetitive member factor. I'm actually going to increase a little bit my strength because there's a lot of members out there that if my stud or something fails, I have another one that can come back up, right? So just to kind of get you going. It gives a lot of flexibility to those out there. Another thing is wood needs to be stamped, all right? If you don't know that it's properly stamped, then try to find a way to make sure that we know what type of wood it is. I was doing an assessment once here for an old structure. There's nowhere to be found what type of wood it was. So I'm not a wood expert. I can't just take a sample and say, yep, this is oak. I had to actually get somebody else to make that determination for me because they were able to actually identify the proper wood species. But with wood stamps, you can get that, right? In this case, you get to see that you got number 2, southern. S means southern dry, southern pine. It's going to be dry kiln. And D fir is Douglas fir. So S dry means that it's just a dry aspect for a number 2 stud. You got construction stud, and you got stand type. Again, Douglas fir, in this case, spruce pine fir, SPF. The other thing here is when you look at panels like plywood, OSB, you're going to see stamps like this. 3216, the main thing for 3216 that I want to let you know out there is that 32 means that it's a span rating for a roof, and 16 is a span rating for floors, all right? So 32 inches, you can span 32 inches with that plywood or that OSB. You can span 32 inches on roof decks and 16 inches on floor decks, all right? Elevated floor decks. That's just important to know. For what you're using it. And it just tells you additional stuff, exposure, and sometimes they will put the actual type of wood, sometimes they won't. So it's just for you to know. Why? Because I told you at the beginning, species is a big factor of this. What type of wood, the grain direction, all this stuff is very, very important. And if you just show up in a building or show up and just see a stack of wood and you don't even know what it is, you don't have the stamps, it's really difficult to do the proper design. So that's one of the drawbacks, right? A lot of species, therefore I got to know which one I'm using so I can make my proper design. Now, when you look at all the materials, I kind of talked to you about the 4 main materials we're going to be using: concrete, masonry, wood, and steel. Various tensile strength, right? 36 psi, 400 psi for masonry. That's a tensile strength. But we look at compression: 1,500 for wood, 2,000 for masonry, 36,000 for steel, and about 3,000 to 5,000 psi for concrete. Unless you start going with high strength concrete, it's different. Density, obviously, you get to see steel is the heaviest, 494 pounds per cubic feet. Wood is very, very light, which is why we like it. And then modulus of elasticity, it kind of varies, but you get to see one thing that stands out is that steel is basically the highest across all four, right? Highest tensile strength, highest compressive strength, but also highest density, which is heavy, and highest modulus of elasticity, right? Whereas if you look at wood, hey, the tensile and compression strength of wood is kind of close, right? That's why we also like wood. We don't need to reinforce it, right? If we're using it appropriately, we can just use wood for both tension and compression. Whereas if I have concrete, I have to make decisions, or masonry, I have to make decisions. It's an flexure, I may have to reinforce, right? So just to kind of put in perspective all we've talked about the common material properties. So hopefully by now you recognize the physical properties pertinent to structural design. Right? I talked about the section properties, material properties, and different aspects of it, how they apply. And finally, recognize the important properties and applications of materials used in structural designs. Basically, there's pros and cons for all the materials. And I kind of went a little bit over the nomenclature of each one: concrete, masonry, steel, and wood. So hopefully by now you get a good startup. So before I leave, as you are getting prepared to come into WENG481, we have all these pre-course lessons for a reason. We want to make sure that you have a baseline of understanding before you get here. This is a very high-paced class. Over 2 weeks, we go over a lot of design aspects and want to make sure that you are prepared and have a basic understanding of different topics, to include, in this case, structural materials. So when you get here, we can hit the ground running. All right, so I appreciate your time, and I guess I'll see you soon.